Let's talk about speeds and feeds. These are very important. All of our CNC machines in the Fab Lab utilize these to some extent. For our laser cutter, we think of speed as how fast the tool moves around on the X and Y axes. But instead of a feed rate, we consider the power at which the laser is fired. Our 3D printers consider the feed rate to be how fast the spooled material is pushed through the hot end nozzle, and speed is like the laser cutter, how fast the nozzle moves. But for our CNC mill and routers, speeds and feeds are slightly different. In this lesson, we're going to identify common cutting tools, learn the definition of speeds and feeds, and calculate the cutting speeds and feed rates. Many different cutters are used during the milling process. These tools you have seen before, but note the same cutting speed formula can be used for each tool. We'll go over that formula on subsequent slides. Here are some other basic cutting tools: a combination drill and countersink, a spotting drill, and a countersink tool. No need to worry too much about these other than to note that there are many types of tools to be used in a mill. Flutes have been mentioned before. This is a 2-flute end mill. You're looking at it from the bottom or end. A tool with 2 flutes has more room for chip evacuation and is usually used for light metals. They tend to be weak and have a short tool life compared to something like a 4-flute, which has more cutting edges and longer tool life. It's used for harder metals, but it can clog easily when being used for deep cuts. Here are some examples to go along with the 2-flute and 4-flute. Again, keep in mind the tools come in a wide variety. Here we see a 1/4-inch 2-flute end mill used for cutting aluminum. It has a shank that needs to fit in a 3/8-inch collet or tool holder, and the length or depth of cut is maxed at 1¼ inches. Notice it has a set of specified applications. Here's the shank. Here's how deep the tool can cut. This part is held by a tool holder or fit within a collet. This one even has a slight groove cut out, as it could click into some types of tool holders. Here's its description and its application. Compare all of this to the 1/4-inch 2-flute ball end mill. Take note of the difference in their shape at the end of the mill. Notice they can be used in similar ways, but not exactly the same. If you used this one for facing, which is making a surface flat and level, you created scallops or divots that are cut along the tool path in the shape of the ball mill. Notice how it has a curved end instead of a flat end. These tools are a bit more specialized. The Countersink and Deburring tool is great for boring the top of a hole that will allow a screw head to sit flush with the material. But it can also use its tip for engraving and its angled cutting edge around the edge of material to deburr it. The other tool does well with 2 of the same applications, but doesn't deburr, and its countersinking is slightly different too. This tool is also really good with light engraving and with spot drilling, an application that means to drill a hole just deep enough to locate a spot that can be used later as a guide for another drilling application. Let's take a look at this cutting tool material and cutting tool geometry set of videos. They're best found on the PLTW courses site under Activity 2.3.2. Activity 2.3.2, Speeds and Feeds, has the cutting geometry and materials videos. We'll start with the cutting tool geometry video.
Several angles are important when introducing a cutting tool's cutting edge into a rotating workpiece. Those angles include the angle of inclination, which when viewed from the side or front, is the angle of the insert seat or pocket in the tool holder from front to back. The angle of inclination may be positive, negative, or neutral. The cutting tool's rake angle is the relation of its cutting edge to the cut itself, and may also be positive, negative, or neutral. The effective rake is a combination of the tool holder's angle of inclination and the rake built into the insert. The largest influence on chip flow in turning is the top or back rake angle. Viewed from the side of the tool holder, this is the angle created by the top of the cutting tool and an imaginary line drawn horizontally through the workpiece diameter. A positive top rake tool cuts freely, with reduced power requirements and reduced temperatures. A negative top rake tool.
In that video, you got to see them using a lathe, L-A-T-H-E. A lathe spins material and engages a tool from the side or the end. That tool will look vastly different than something that's used in a mill. The tools that you see here function in a similar way that the mill does, but the mill will spin the tool at high RPMs, whereas the lathe will spin the material at high RPMs. Now let's look at cutting tool materials.
The main objective in the selection and application of cutting tools is to safely machine a workpiece in the shortest possible time while meeting the part's quality requirements. There is no ideal cutting tool material, but the rapid evolution of tool materials has given us a wide choice to meet any need. High-speed steel tools are commonly used in tool rooms and in low-speed operations. Round tools such as drills, taps, and end mills are commonly made of high-speed steel. Coatings have extended the applications and cutting life of high-speed steel tools. Carbide tools, particularly coated carbides, are today's most common cutting tool material. There are a great variety of carbide compositions and coating types. Carbide tools may be indexable inserts, or solid round tools such as small diameter end mills or drills. Coated carbide inserts are the first tool material to consider for most production operations. Most insert coatings have multiple layers to protect the tool against abrasion and chemical wear. Ceramic inserts may be alumina-based or silicon nitride-based. They withstand higher heat than carbide, have good resistance to abrasion, and they cut very fast. But ceramic inserts are less shock resistant than carbide tools, so their applications are limited. Cermets are composed of titanium carbide or titanium nitride with excellent resistance to various forms of wear. But cermets do not withstand high heat well. The super hard materials are cubic boron nitride, CBN, for ferrous applications, and polycrystalline diamond, or PCD, for non-ferrous applications. Both materials are expensive, but can outlast carbides by 10 to 100 times.
This video did a great job of showing you the types of materials that tools use. Not that tools cut through, but that tools use. These tools are made from some very strong, very durable types of materials. Some are composites, some are just a type of tool that's been coated in a material to strengthen it. We need to define a few things before we move on to calculating feeds and speeds. Cutting speed is the rate of a tool measured in surface feet per minute. Cutting speed must be converted to inches per minute so that it can be expressed as RPM. This gives us the spindle speed, the number of revolutions per minute, or RPMs, that is made by the cutting tool of a machine. Feed is the distance advanced by the cutting tool along the length of the work for every revolution of the spindle. Feed, or chip load, must be converted to inches per minute to give us the feed rate. Spindle speed is defined as RPMs. We find this by dividing the CS, the cutting speed, which is obtained from a machinery handbook, by the circumference of the tool. A revolution is one complete rotation. This distance is called the circumference. The circumference of a circle is found by the formula pi d, where pi is the constant value of, well, 3.14, approximately, and d is the diameter of the circle. In our formula, the diameter is used that of the tool being implemented. Since cutting speed is defined in feet per minute, while circumference is defined in inches, we have to convert so that the units match. So we multiply feet by 12 since there are 12 inches in a foot. Spindle speed is determined based on the materials to be cut. If the spindle speed is too fast, the tooling will wear out quickly, which can be expensive. If the spindle speed is too slow, then time is wasted. The cutting tool can actually bond to the material at slow speeds, which can damage equipment and be quite costly. Pause the video and take a moment to record this equation and what each one of these letters mean. N, spindle speed in RPMs. CS, cutting speed in surface feet per minute. We have to convert it to inches per minute. Diameter of the tool in inches per revolution is your D. In the end, this can be simplified to spindle speed as being the cutting speed, once it's converted, divided by the circumference of my tool, pi times the diameter. Here are some recommended cutting speeds. Notice how the speeds are slower as you move down the chart. Why is that? Well, the materials are harder as you go down the chart. Note aluminum, 250 feet per minute. Note brass, 150 feet per minute, and copper, 100 feet per minute. Even mild steel, 90 feet per minute. But you get down to really dense material like titanium and high manganese steel, and you're at 50 and 30 feet per minute, respectively. Let's run through an example. What spindle speed should be used to mill aluminum with a 1/2 inch end mill? We start with the formula and substitute the known values. Note that the spindle speed used 3.14 instead of all of pi, and then was rounded down instead of following the traditional mathematical rules for rounding an answer. Rounding down results in a more conservative spindle speed. The difference, however, between 1,910 RPMs and using the pi function on a calculator and getting 1,009 RPMs is negligible. Conversely, expert machinists know how to find so-called sweet spots of high speeds and feeds that any small fluctuation from exact values could destroy the tool or material. Let's do another one. What spindle speed should be used to mill brass with a 1/4 inch end mill? Pause the video if you want to try solving for this 1/4 inch end mill used with brass. Did you get 2,293 RPMs? we take the 150 feet per minute for brass as its cutting speed. We convert it to inches per minute by multiplying it by 12, and then we divide, important to use parentheses here, some version of pi, PLTW will use 3.14, times 0.25 inches for every 1 revolution. That gives us our circumference. So we have a converted cutting speed divided by our circumference to give us a spindle speed, how fast that tool should spin, 2,293 RPM if I want to get through brass or bronze. So that covers the basics for speed rates. But what about feed? Let's calculate some feed rates now. Here's the basic equation. Fm, the feed rate, in inches per minute is equal to Ft, the recommended tool feed value, which is provided from a table and given as inches per tooth of revolutions, times Nt, the number of teeth, that's cutting faces, aka the number of flutes on the tool. This is a unitless number. Times capital N, also known as the spindle speed, which we just learned to calculate as the cutting speed converted to RPMs. Pause the video and take a moment to copy down what you see, the formula, and all of these letters. It's important to note for each of these variables that you're writing down what the units are so that you don't forget that you do need to convert in some cases. Much like with CS or cutting speed, we have a recommended tool feed. Notice that there are 3 feeds for each material on this table, depending on whether it's a face mill, which is often a large area being cleared and leveled from above, a side mill, engaging the side of the tool into the material laterally, or an end mill, which could be engaged in a pocket or profiling, removing material with the end and side of the tool. Also, each material has a range of values attached to it. Typically, you're going to use the smallest value just to be cautious. You aren't an expert after all, so that sweet spot isn't something you're shooting for. You're shooting for conservative values. Let's do a feed rate example. Calculate the feed rate for end milling aluminum with a 2-flute, 1/2 inch HSS end mill. HSS stands for high speed steel. What is the tool feed for aluminum? Here's our equation. Here is our Ft. We'll come back to these. Notice that we're using a pretty conservative value, 0.005 instead of 0.010 or anything in between them. We are using the end mill column, however. First, we need to calculate the spindle speed. Earlier, we used 250 feet per minute for aluminum and found that we needed 1,910 RPMs. With our tool feed that we found on the previous table and number of teeth, which we know from the example problem, we plug in the spindle speed and get 19.1 inches per minute for a feed rate. Take a moment, pause the video, and look over this math. Notice we did the exact same things for spindle speed, and then we simply plugged in what we knew in a very simple multiplication problem. Okay, hopefully you've taken enough time to copy down what you need. All of this means that if we want to end mill an aluminum workpiece with a 2-flute, 1/2 inch high-speed steel end mill tool, we have to rotate our tool at a speed of 1,910 RPMs and have it moving through the material at 19.1 inches per minute. Now that isn't very fast when you consider that we can move through machinable wax at around 3,000 or 4,000 RPMs and near 40 inches a minute. our mill can speed up to 10,000 RPMs and move at around 100 inches per minute maximum. Our CNC routers can engage material at 18,000 RPMs and feed through the material very quickly as well. But we're dealing with a metal, with aluminum, and that metal is more dense than something like wax. Okay, let's do another one. 1,910 has been rounded. It is actually customary to wait until the end, till the last step, to do your rounding. Keep that in mind. Let's calculate the feed rate for face milling aluminum with a 4-flute 1/2-inch HSS end mill. Aluminum, 250 for the feet per minute cutting speed. Here's our formula. Here's our math. We take that 1,910 and we plug it into our feed rate equation along with our feed per tooth, so 5/1000ths of an inch per tooth of revolution, and how many teeth we're using. In this case, a 4-flute has 4 teeth. 0.005 times 4 times our 1,910 RPMs gives us a feed rate of 38.2 inches per minute. Feel free to pause the video and take a moment to record this example. Let's move on. We can mathematically calculate the feed rates, but other factors affect the feed rate as well. Power of spindle motor, condition of cutting tool, depth of cut, quality of surface finish that's required, roughing versus finish cuts, there is a vast difference, condition of the machine that you're using, how old is it, how beat up is it, the strength of your fixture that's holding your material in place. The feed rates can also vary. We could be dealing with, say, a plunge feed rate. Plunge feed rates, driving down into the material from above, use the same formula. You just go half as fast, so you divide by 2. Take a moment to record this if you need to. Let's use a plunge feed rate in an example. Let's calculate the plunge feed rate for plunging into mild steel with a 4-flute 1/2-inch HSS end mill. On the table where we found the aluminum CS, we could also find that mild steel. It's typically 90 feet per minute. Remember, we round down, so we're using 687, not 688. Then we calculate the plunge feed rate, and again, we used a table to find the most conservative tool feed, and we found it to be 0.002 inches per tooth of revolution. This results in 2.7 inches per minute when we have divided by 2. Let's calculate another one. Find the plunge feed rate for plunging copper with a 4-flute 1/4-inch HSS end mill. Same process. 100 feet per minute for copper is found on a table, plugged into the spindle speed, then somewhere around 1,529 RPMs should be used. Note that the same formula is used, and we just need to find the feed value. And voila, 24.5 inches per minute. Take a moment and copy it down if you need. As we wrap up, let's be reminded that there are some special operations. There are some circumstances that require speeds slower than the ones obtained from our basic formula. Let's read through them. Reaming, 1/2 to 2/3 of that we used for drilling the material. Counterboring, 1/4 of that used for drilling the material, and countersinking is also a quarter of that used for drilling the material. In tapping, which is threading a hole, there is no real special formula. It's determined by many factors and usually ranges from between 50 to 300 RPMs. And finally, do remember, all of this can be found on your formula sheet.